So let's connect this to what we've done so far in 2D. In 2D, we were looking at rotations about the z-axis, x0, y0. And so if you turn the frame by an angle theta, then you'll end up with a new frame, x1, and that is oriented at an angle of theta with respect to the original x-axis. And if that rotation is done in time t, then you say the angular speed is omega, which is theta dot, right? So in 2D, the angular speed is in the z direction. We always ignored z, but it's actually in z direction, as you can see. And this rotation can be written as theta dot, rate of change of theta. And the k denotes a vector, which tells you the direction of rotations. This is a unit vector in the z direction. Also in 2D, we looked at the velocity. And I did not quite write it in this form, but the velocity can also be written as a vector. It's v equals omega cross r, okay, where this cross is the cross product. Okay, in case of 2D, what we actually did was we did not use the cross product, but we showed that it can be written as J, which is a Jacobian, times Q dot. Okay, but these are the same things. It can be shown that JQ dot is the same as what you get if you do omega z times cross r. Okay, so the first one is angular speed, the second one is linear speed. Now that we know we've set down what we did for 2D, let's do 3D. Okay, let's assume that omega can be written in 3D as, so omega z here was theta dot k, but let's say that the generic angular speed in the x, y, z direction can be written as omega x, omega y, omega z. And since they are in their own respective directions, let's put ijk, where ijk are unit vectors in the x, y, z direction. Similarly, the position vector in case for a generic 3D case can written as rxi plus ryj plus rzk. Okay, now that we've said that, let's try to understand what we can do with omegas and v's in 3D, and that's what the whole class is going to be dedicated to. So in 3D, v equals omega cross r is still true. Same in 2D, right? We wrote that, and that's true. And so what we can do here is we can write the velocity now that omega and r are no longer planar. Omega is omega xi plus omega yj plus omega zk crossed with rxi plus ryj plus rzk. And this is the cross product. I'm pretty sure you can symbolically compute this using SymPy. Okay, however, I'll show you that you don't really need the cross product. You can actually write that in terms of a matrix. Okay, and that's going to be a useful thing for us eventually. So I'm going to first do this cross product like you would do it using pencil paper. Essentially, you write ijk, then you write the first vector, omega x, omega y, omega z, and then you write the second vector, rx, ry, rz. And then all you need to do is take the determinant of this quantity, and that would be, you can expand it along any row, any column. Just advantage is to do it along the first row because you have I, j, k there, so you get the I, j, and k components. So to compute the I component, you essentially hide the row and column corresponding to I. So ijk, you hide it, I, omega x, rx, you hide that, and you'll be left with this 2 by 2 matrix. And so you just take a cross multiplication. So you find the determinant of that. So that would be omega y rz minus omega z ry. Then the expansion says that you need to do a negative of j, and then you will hide the corresponding row column. So ijk and j omega y ry. And so you'll have this. So you have a determinant formed by that. Compute the determinant of that 2 by 2 matrix. So that would be minus j omega x rz minus omega z rx, and then same thing for k. Omega x r y minus omega y rx. Okay, so you can see that this is basically a vector. It has an I, j, k, and that is what you would expect because velocity is, after all, a vector. Okay, now I'm going to show you a simpler way of doing the cross product using matrices. Okay, and this is something which we'll be using in the course. So let me just show it to you. First, we need to define what are known as the skew-symmetric matrices. So a skew-symmetric matrix is something which, if you take the transpose, if you take the transpose, it becomes the negative of the original matrix. Skew-symmetric matrix. Definition is, if you have S with some argument A, and I'll talk about A is in a bit, equals the negative transpose. So if you get the transpose on the other side, you have basically this identity. That's the definition. A consequence of this definition is that all the diagonal elements of a skew-symmetric matrix have to be 0. So a generic form for S of A is this. Zero minus AZ, AY, AZ 0, minus AX, minus AY, AX 0. So you can check if you take the transpose of that, then you will find that transpose is the negative of S of A. Okay, so the property, the two properties which we would need in this class. First one is that if you have two vectors, A cross B, where A is has three elements along X, Y, and Z, and B is similar to that, then you can actually write this as S of A times B. Here we'll check this in fact. The other property is if you have a rotation matrix and you multiply it with S and then R transpose, then this is the same as S of R of A times B. Rotation matrix. Yeah, so the proof of that is slightly more involved. I would not prove number 2, but I'll show you that one holds true. Okay, so this particular expression A cross B equals S of A times B is very useful because now you can take a cross product and write it as a matrix S of A times a vector B. And so one place where we can verify this is we've already computed omega cross R, that is A cross B. This identity says that you can also write it as S of A times B. So let's just do that and then compare it to what we had earlier. So S of A times B, or S of omega R is the same as omega V equals omega cross R is the same as S of omega times R. So I need to write the skew-symmetric matrix, omega Z. So I just substitute A with omega, that's what I'm doing. Omega Y, omega Z 0, X minus omega Y, omega X. Okay, and then R is Rx, Ry, Rz. And so now that we have this vector, matrix times vector, we can carry out the the multiplication. So we would have minus omega Z Ry plus omega Y Rz. That's the first row. Omega Z Rx minus omega X Rz. And then finally minus omega Y Rx plus omega X Ry. Okay, so now we can actually take this and compare it with what we had got for omega cross R. So this example, this is what we had for the first element, that is of I. It's omega Y Rz minus omega Z Ry. And you should see that it's the same here, omega Z Ry minus, it's written the other way, omega Y Rz is second and then minus omega Z Ry. Then if you look at the second one, omega X, so there's a negative sign here, so we need to take the negative inside. So we'll have positive omega Z Rx minus omega X Ry. So omega Z Rx minus omega X Rz. And then you can check the third one too, it should be the same. Okay, so that checks with okay, so we can safely use that. So we really don't need the cross product. We can just use skew-symmetric matrix to carry out this cross product. Okay, so this is basically a starting point for something else later on. This is all about linear velocity. That is, the linear velocity is omega cross R, and that's true not only in 3D, but also in 2D. Okay, that's the same identity is true. Now let's move to the angular velocity. So we have omega Z equals theta dot K, right? And that theta dot is the angle turned about the Z-axis. Now, how did we write the angle turned about the X, Y, and Z-axis? We used the Euler angles. We had theta as the rotation about sorry, phi as the rotation about the x. So we looked at 3 to 1 Euler angles, in which you first rotate about the z-axis, then y-axis. Let me highlight that here. So first z-axis, so you see this rotation, then y-axis, see this, and then z-axis. Sorry, z-y-x, my bad, x. Okay, so the rotations are psi about z-axis, theta about the y-axis, and then phi about the x-axis, right? And so you would think that if you did this sequence of rotations and speeds, then just like this expression, maybe the formula for angular, a good guess would be the angular velocity is omega equals, so it was phi about x, theta about y, and psi about k, right? Those were the Euler angles, and so these were rate of change of Euler angles. Rate of change of Euler angles. However, it turns out that this is not true. You cannot write omega as the rate of change of Euler angles in I, J, and K. The actual relation is much more complicated. It is because of the fact that, and we've done this before, that rotations are not, in 3D are not commutative. That is, if you rotate by theta 1 and theta 2, and then reverse the rotation from theta 2 to theta 1 about two different axes, then you will see that the final orientation of the object is different in both cases. And that's why you just cannot write this expression. This is because rotations are not commutative. Okay, so the question is, what is the angular velocity? And it's important to know the angular velocity because unless we know the angular velocity, we cannot do things like, for example, we can't compute the Jacobian, we cannot compute the linear and angular velocity to compute the energy, which then goes into computing the equations of motion. Yes, so I'm going to show you how to compute the angular velocity in 3D. And I think that this particular part there's a little bit of derivation. It's kind of important to know how you actually do that, because there's some things where you can just remember the final equation and then go ahead. But for something like this, it's very fundamental that you want to understand how to compute this omega for any any set of Euler angles, x, y, z, z, y, x, z, z, y, z, and so on. So it's important to understand the derivation, how it comes. So I'll take the effort to derive the expression. Okay, so next we're going to look at angular velocities in 3D. So for 3 to 1, so we'll derive the angular velocity for 3 to 1. So angular velocities for 3 to 1 Euler angles. Okay. So I'm going to start with a very non-intuitive place, but the whole point of doing this is to understand that the angular velocity comes from the rate of change of angles, and the rate of change of angles, that whole Euler angles, is embedded into the rotation matrix. So we'll start with the rotation matrix and do some manipulations and then see what the rotation matrix, the rate of change of rotation matrix gives us. You'll see that the rate of change of rotation matrix actually gives you some information about the angular speed. So let's start with this identity. Yeah, so that's true for any rotation matrix. In this case, in particular, I'm looking at the rotation matrix for the Euler angles, 3 to 1. It can be any angle. It's not, at this point, I'm still very general. I've not really looked at 3 to 1. This holds for anything. So let's differentiate with respect to time. So we have R dot R transpose plus R dot transpose equals the derivative of identity is 0. Okay, so now I'm going to do some manipulation. Okay, I'm going to write the transpose of transpose. So I'm going to have two transposes here. Because if I take the transpose 2 times, then I'll end up with the same matrix, right? S transpose of transpose is the same matrix. So I can do that. And now what I'm going to do is, I'm going to use the fact that AB transpose is the same as B transpose, A transpose. So now I can write this as R transpose, R dot. No, I'm doing it wrong. That'll be R dot. So transpose of R dot transpose R dot, and R transpose. Times transpose equals 0. So note that I've taken care of this part only. I've kept this transpose as is. Okay, now what you notice is that if this is a matrix, the same matrix appears here, but then the sum of the matrix and its transpose is 0, which means that that matrix, R dot R transpose, has to be a skew-symmetric matrix. Because for a skew-symmetric matrix, S plus S transpose is equal to 0, right? So this is S of A plus S of A transpose equals 0, where S is skew-symmetric matrix. Okay, so I don't know what A is, but I can tell you that A has some bearings with the angular speed, as you'll see in a bit. So what I've done is I've written S of A as R dot R transpose. And remember that R dot is probably related to the angular speed because it gives you the rate of change of the Euler angles in a way, because Euler angles are embedded inside R. Right? So we can write an expression for R dot now that we have this expression. So I wrote R dot R transpose is S of A. If I post multiply with R, then I would have R dot R transpose R equals S of A times R. And then we know that R transpose R is identity. So R dot equals S of A. So this tells you that the rate of change of the rotation matrix is that skew-symmetric matrix times R, where we still have to interpret what A is. We don't know what A is yet. Okay, now we'll try to establish what A is. Okay, so for that, what we'll do is, we know that the position of any point of the body, x0, y0, this is the bad notation. Let me just write it this way. Imagine a generic body, frame x0 is a point. In body frame, then the position in world frame is the rotation matrix times the one in body frame. Okay, I think I proved this last time. This was right here. So position in body frame, if you take the rotation matrix, multiply with the body frame vector, then you get the position of the same body of the same vector in the world frame, right? So I wrote the same thing down there. Okay, I just skipped the, removed the R0. So what we can do now is, once we have this, we can differentiate this with respect to time. With respect to time. Then we have R dot equals R dot RB plus R times RB dot. Okay, now RB is the position of the body in body frame, which means that when the body, so if there's a body and there's a vector in the body frame, as the object turns, that vector also turns with it. So it's in body frame. It's fixed with respect to the body. Okay. Since it's fixed with respect to the body, it's not changing with respect to time. And so I can put that equal to 0. So I have R dot equals, small r dot equals capital R dot times B, RB, but I know that R dot, let's call this 1, from 1, R dot equals S of A, so R dot is S of A times R times RB. Okay, but R times RB is something we already have. From here, it's called this 2. So from 2, R dot equals S of A times small r. Okay, we'll write that again. So I have R dot equals S of A times R. Okay, but we know something about S of A. I hope this isn't, everything is fine. Okay, so S of A times R, but we know something about S of A times R. If you have Skew-symmetric matrix times R, you can also write this as A cross R, right? Because we already showed that S of A times B is the same as A cross B. But then we also know V equals omega cross R. Okay, so it has to be that A is nothing but the angular speed. Let's call this 3, 4, from 3 and 4, omega is nothing but A, which means that we can now write R dot R transpose is S of omega, or R dot equals S of omega times R. So the angular speed is related to the rate of change of R. Okay, but that still doesn't answer the question, what is omega in terms of the Euler, rate of change of Euler angles? Okay, so that's something we'll come to next. So what is S of omega? It is a skew-symmetric matrix with this form, 0 minus omega z, omega y, z0, x, omega x. Yes, so how is omega x, omega y, omega z related to phi dot, theta dot, psi dot, rate of change of Euler. Okay, so we'll do the next. Okay, now we're going through a slightly elaborate derivation of figuring out how omega is related to the rate of change of Euler angles. Okay, so we'll start with the definition of S of omega. It's R dot times R transpose. We know what R is based on Euler angles, so we'll expand that out, and then whatever comes out will give you the relation between omega and Euler, rate of change of Euler angles. Okay, so S of omega is R dot R transpose, but we know that R is RZ psi. We don't need this RZ RY RX. So this is 3, 2, 1. Yes, for the homework, I give you a different sequence, 1, 2, 3, and I told you to do the same derivation. I'll show you two methods to do the derivation. This is like from first principle. If you like math, then you can use this method. You might be able to do this symbolically. The other method is more intuitive. You can just look at the transformations and then write it by hand in like one line. Okay, so let's do this. So we have R dot. Let's sub in the value RZ, RY, RX. The whole thing should be differentiated, and then RZ, RY, RX with transpose. So when I take the derivative, let me just actually simplify this first. RZ, RY, RX, the whole dot. And then when I have RZ, RY, RX transpose, all I need to do is to take the right RX, RY, RZ with the transpose in each of them, just like you do A, B, transpose is B, transpose, A, transpose. So you can just apply that in sequence. So I get RX transpose, RY transpose, RZ transpose. Okay, and then now let's take the derivative of that expression. Now, remember that I need to apply chain rule. I need to first take the derivative of the first term, keep other two constant, and so on. So there'll be three terms emerging from the derivative term. So they would be as follows. There'll be RZ dot, RY, RX, plus RZ, RY dot RX plus RZ, RY, RX dot. So all that is a part of that derivative. And then I have RX transpose, RY transpose, RY transpose, RZ transpose. Okay, so let's do it one by one. Let's call this 1. Let's call this 2. And let's call this 3. So I'm going to try to attempt to simplify all these three terms individually. So we'll do this 3 times, and we'll probably get the answer to the question, what is omega in terms of Euler rates? So the first term, we have RZ dot RY RX, but you should not forget these which are outside. So it's going to be RX transpose RY transpose RZ transpose. Now you notice that Rx times Rx transpose is identity. Okay, after you do that, you'll see that you have R by transpose that is also identity. And so you'll be left with RZ dot RZ transpose. Okay, but what is R dot times R transpose? It's just S of omega Z, right? Which is S of, so what's the angular speed about the Z axis? It's simply psi dot K. As R dot R transpose is S of A. So I just wrote the corresponding rotation. So that is S of psi dot K. Okay, that's the first one. Let's do the second one. Okay, so we have RZ RY dot RX. Number 2. RZ RY dot RX. And then I need to also multiply it with this term which is left over. So RX transpose RY transpose RZ transpose. Okay, now first thing you notice is that RX transpose is I. And so this would simplify to RZ RY dot RY transpose RZ transpose. Now, one thing you would remember is R dot Y R transpose is nothing but S of the corresponding rotation corresponding to Y or omega Y. Right, so that is, so the rotation about the Y axis is going to be theta dot J. So I can write from here RZ S of theta dot J RZ transpose. Now there's another property I need to use, which is, I wrote it down, but I did not prove it. So this is the property. R times S of A times R transpose is S of RA times. Where did the B come from? Yeah, it's not right. It should be S of R of A. There's no B. So R transpose is S of R of A. Let's use that. So R S of A, R transpose is S of R of A. And I'm going to use the same thing here. Write this as S times RZ times theta dot J. Good. Okay, so that's the simplification for the second one. It boils down to RZ theta dot J. Okay, one more left. Third one. The third one was RZ RY RX dot And then there was things outside the bracket, which was Rx transpose, Ry transpose, Rz transpose. So again, I can use the fact that this is S of omega x, which is S of the rotation about x-axis is P dot I. And so I would have Rz, Ry, S P dot I, Ry transpose, Rz transpose. But now I can use this property that R times S of A times R transpose is the same as S of R of A. So this becomes S of Rz, Ry. Okay, if you think it's easier, you can write it like this: Ry, Rz. Yeah, I just wrote Ry transpose Rz transpose is B transpose A transpose, same as A B transpose. So this, and so now you can see how that's related to that Rs R transpose. Okay, so let's see what we have. We have this thing, we have this thing, and then we have the one on the previous page. So I'm going to put all this together. Yes, I'm going to put all of them together. And that's going to give me what SW is, right? So S of W is the following. Number one is simply S psi dot K. Plus RZ times theta dot J. And then finally, S times S of RZ Ry P dot I. Okay, now, if you have sum of skew-symmetric matrices, then you can just add them together. Just like think of that S matrix as that matrix. If you have three matrices, then you can just add them element-wise, right? So what I can do is I can club all of them together and write S of psi dot K plus RZ theta dot J plus RZ Ry P dot I. And this is the expression I was after. Omega equals psi dot K plus RZ theta dot J plus RZ Ry P dot I. So you see that it's not simply psi dot K theta dot J P dot I. It is something more complicated. It has RZ and RZ Ry in it. Okay, so for this, what we did was we basically used the definition and then went about writing, simplifying each of those expressions and getting the final answer. Now I'm going to show you a shorter way, and this way is good if you are a person who likes to visualize. It also will let you quickly compute the angular speed, the angular velocity for any set of Euler angles, 3 to 1, 1 to 3, whatever you want. And it is a little bit more graphical. So if you like to visualize. Okay, so for that, I'm going to borrow something I wrote down earlier. So this is angular velocity another way. So this is the sequence of rotations to get the Euler angles 3, 2, 1. Okay, so mark it this. Okay. Okay, so now I'm going to write basically this equation for angular speed just by looking at that figure in 2 lines. Okay, it's as simple as that. So angular speed is, remember, it's about different axes. The first one is about the z-axis. So psi dot k, or let me put it as z. Next one is about this new y, and the rotation is theta dot, but it's about y. And then the final one is phi dot about x. Right? Okay, so although ijk is not true, this is true because these rotations are over the new axis. Okay, now all I need to do is try to relate how z, y prime, and x double prime is related to ijk, and I should be done. So z is, so remember that this is also I, j, k, right? So the first one is clearly about k. Right? The second one is plus theta dot about y prime. Okay, now the question is, how is y prime related to ijk? So if you want to go from y, from this configuration to this one, what you need to do is you need to rotate this frame by an angle of psi, okay, to get the new frame, which is shown here. So any vector which you have in the left, you need to multiply it with r psi or rz in order to get y prime. So y prime is rz times y. Just that's the definition of the rotation matrix. So then this is going to be rz times y, which is going to be j, plus phi dot. Now for x, what I need to do is I need to go from, if I want x, I need to go through this frame and this frame, but this one is rotation about the y-axis, and then I need to do rotation about the z-axis. So that boils down to saying rz, ry. Right. And the reason I did rz and ry is because in order to go from here, I first need to go to this one. So I first pre-multiply with ry, and then I need to pre-multiply with rz, so that the order is consistent. I go from this configuration to the middle one, and then the last one. Okay, so the angular speed is psi dot k plus, since theta dot is a scalar, I can write it as, I can keep it anywhere I want. Okay, and then you can check this with what I got earlier. Should be the same. Same. Okay. Now there is another good thing about writing it using this form of derivation, which is this is world frame angular velocity. Okay, it's the angular velocity in the frame ijk, but sometimes I'm interested in not the angular velocity in world frame, but angular velocity in the body frame. Okay. What that would mean is I need to compute the angular velocity in this frame. So what I'm going to do is I'm going to use a similar technique, which is instead of writing omega as a function of, so omega will be omega body frame as a function of ijk, where ijk are in the fixed frame, this one, I'm going to write it as in this frame, which is the body frame. So it will be in terms of, let's create a new one, I prime, j prime, k prime for that, and then try to write everything in terms of that. Let's copy this figure again. I prime, j prime, k prime. Right here. I prime, j prime, k prime in this configuration. Now, I want to write the angular speed in the body frame. Okay, and I'll try to write in terms of I prime, j prime, k prime. So for this one, I would have phi dot about x double prime plus theta dot about y prime plus psi dot about z. Okay, the same. This is exactly the same as before. Only thing I'm going to do is I'm going to change my way of representing ijk to I prime, j prime, k prime. So phi dot x is same, x double prime is same as I prime plus theta dot. Now over here, what I need to do is instead of going from the leftmost, this one to this one, we want to go the other way, which is we want to go this way. And for that, we need to take, instead of taking the matrix R, which we went when we went forward, we need to take the inverse so that we can, instead of going positive or clockwise or counterclockwise, we go counterclockwise in order to make that happen. So that happens when you take the inverse, but the inverse for rotation matrix is the same as the transpose. And so we can write this as R transpose of that corresponding rotation. So this, if you want to go from here to here, you need to rotate about the x-axis and the inverse. So that inverse is the transpose. And so you'll write R transpose times J prime. And then this one would be two of these, Rx transpose, Ry transpose, Z would be K prime. And then this would be psi dot. So omega in body frame is theta dot I prime, Rx transpose J prime plus psi dot Rx transpose Ry transpose. Okay, one more thing before I finish. You can actually simplify this expressions. Instead of writing them as vectors, which we have not really done in this course, you can actually write them as a matrix, cos psi, cos theta, sin psi, minus sin theta, minus sin psi, cos psi, 0, 0, 1 times the rate of change of Euler angles. You can also do the same thing for omega b. It comes out to be 1, 0, 0, 0 cosine phi minus sin phi minus sin theta cosine theta sin phi cosine phi cosine theta phi dot theta dot psi dot. Okay, so you can write it as omega equals A times, we call this the vector of Euler angles, and omega B equals AB Euler angles. Okay, so this is basically telling you that you can write omega and omega B as a function of the Euler rate of change of Euler angles, rate of change of Euler angles. Okay, so in typically a problem, what will happen is you will either you will know the Euler rates and you'll compute omega, or you're given omega, you'll compute the Euler rates. Now, if you want to do the reverse calculation, this is, if you're given the Euler rates, then omega is simple, but if you want to compute theta dot given omega, then you need to be very careful about A inverse, because A inverse can become singular, right? If it doesn't become singular, it's good, but if it becomes singular, it will be a problem. Just like for the manipulator, there was this singular solution. So it turns out that A inverse and A inverse B is actually singular when cosine theta equals 0 or theta equals pi by 2. That is, when the middle angle becomes 90 degrees, you will have a singularity. So what it means is that there's nothing bad going to happen to the object. It's not like for a singularity for the manipulator, that's a very bad configuration. It is infinite speeds. But for the manipulator, for the rigid body in this case, nothing bad happens physically, but your calculations will become messed up if you use A inverse for calculations when theta becomes 90 degrees. So in order to avoid that, you want to use what are known as quaternions. Use quaternions to avoid singularities. Okay, so nobody really uses Euler angles to represent rigid body motions. They usually use quaternions. So we will not talk about quaternions, but that's something which you would typically see in software. So if you look at MuJoCo, I've not really talked about 3D, but MuJoCo uses quaternions to represent three-dimensional rotations, not Euler angles. It uses Euler angles for other things.